chapter 14, right? So we're going to be launching into chapter 15 then today. This is a big one. This should be a review topic from Algebra 2. It's another topic you have not seen before, so we'll take our time going through this. This tends to be a difficult Algebra 2 topic, maybe the most difficult second semester topic for the traditional Algebra 2 student. So just as a fair warning, like put on your big boy math pants.
They're on.
Okay. Those of us that are the seniors in here, we won't. Obviously, we're not. You guys will not finish this before your guys' last days. So we'll. It'll be like the parts of this topic that would be represented on your exam would just be the stuff that you've completed. Okay. So it's not going to be. I would not ask you to go on and do more than what we did in class. It'll just kind of stop. And we'll try to make that clear as to when it comes time to talk about what would be on your senior exams, what that would include. Okay. So, chapter 15 is concerning 3 different types of functions. So we're going to be talking about exponential, logarithmic, and logistic functions. Those are going to be like the 3 major topics that we're going to look at here. So we'll take some time talking about each one of these types of functions separately. And then at the end of this chapter, we'll look at some like applications specifically in the areas of finance. So this will be, I don't know, there's like 7 or 8 sections or something in this chapter. Let me look real quick. There's 5 sections, but most of, again, like some of these are quite big sections. So, all right. And I'll probably go ahead and I'll probably do a little bit of filler also, since this is your first time seeing these topics. So there'll be some places where I elaborate more so than what's in the textbook or in the homework. Again, because I know it's the first time we're doing this, just like I did last chapter. We did more than what was kind of in the lessons, because I know it was the first time seeing it, so I wanted to cover some of those other topics in a little bit more depth. Okay. So, first thing we're going to be talking about in section 15:1 is exponential and logistic functions. So when I talk about an exponential function, this is something that we can write in the form a times b to the x, where we have a couple of requirements here. Our value for a cannot be 0. Why can't a be 0?
If you times something by 0, it's 0.
Because if I times something by 0, it's 0, and that would be a constant function, which is a type of polynomial, not what we want to classify as an exponential. And b has to be a positive value and not equal to 1. Why can't B equal 1? Let's start there.
One squared is always
1 to any power
yeah, one to any power.
is always 1,
That's
which
right.
would make this thing simplify down to just A, which is a constant function, so we don't want to include it that. Why does B have to be positive?
Because you can't have a negative.
Well,
Actually, no.
B is not the exponent though. B is the base of the exponential.
You can't be a negative.
Why can't B be a negative?
I don't know. Actually, isn't it?
That is what the shape of the graph looks like.
Yeah.
And it can go down.
Yeah.
That's okay.
I don't know. I'm lost.
Okay. So let's just imagine what,
If it's exponential, we're trying to make a growth because if we go negative, then we make no money.
well, what if B is negative 2
Go off.
and A is like 1, right? Let's just pick something simple. So we'd have some function like this, right? What would happen if I did f of 1? I would just get negative 2, right? So that's no problem, right? Doesn't seem like that's a big deal. If I did f of 2, I would get 4. If I did f of 3, I would get negative 8.
That's for apple what, right?
Mm-hmm. So this is kind of weird. What's going to happen for every f of any even number? What am I going to get? Positive. What if I get f of any negative number or odd number? I'm going to get negative. That's weird, right? But that we could live with. Here's the part that's bad. What if I do f of 1/2? What is a 1/2 power the same as? What is the exponent of 1/2 the same as? Okay, so 1/2 is the same as 0.5, but the exponent of 1/2 isn't the same as 0.5. What is the exponent 1/2 the same as? Okay.
The square root.
That is it. Thank you, boy.
That was good.
So that would be 1 times the square root of negative 2. What's wrong with that?
It's not real.
Yeah. Yeah, that's going to be non-real. And that's the big problem, right? We don't want to have any even or fraction with an even denominator is going to create a non-real result. So that's going to be like, there's be like a hole or an asymptote or something in my graph. And how many fractions are there with even denominators? Infinitely many of them, right? This is starting to look like a tremendously bad idea. Everybody kind of agreeing with that?
Agreed.
So this is why we're not allowing B to be negative. One, you're getting that bouncing behavior where the values are bouncing between positive and negative. That's stupid, but we could live with that. What we don't want to deal with is the lack of continuity, right? Where this has infinitely many discontinuities. That's a major, major problem. This is an enormously disgusting looking thing, right? So that's the behavior we don't want it to have. So let's think about what are the end behaviors for this going to look like. So what if we're talking about our end behaviors here? Right? Since we've disallowed b to be negative, we know that this function is going to be continuous everywhere for all values of x, because you can always take a number and raise it to a power, as long as the base number that you're doing that to is non-zero, right? That's always going to be possible. So we're going to have something that's continuous. So the end behaviors, we're really just concerned about what happens when x gets really, really big and what happens when x gets really, really small. Okay. So what can we say about this then? So we have some exponential function, right? Y equals a to the b. The first limit we're asking about is what is that graph doing when I'm plugging in bigger and bigger and bigger numbers for x? What is the picture of the graph doing, right? So it's what's happening to the arrow at the end of the graph. Which way is it pointing?
Positive.
Okay, so Nathan says positive. By that you mean which direction though?
To the right or up.
Up and to the right. Okay, so let's just take a little quick peekarooski. So I'm just going to make A1 and B2. Let's just do that. So that seems to match what Nathan was describing. But let's say what happens when we pick a value that's less than 1. Right? So it appears that two things can happen, right? This will go to positive infinity for b's greater than 1. And it'll go to negative infinity for b's. I'm sorry, we'll go to 0 for b is less than 1. Those two are starting to bleed together a little bit. I'll just draw on a little divider there. So far, so good. Okay. What's going to happen as the x's get really, really small? Let's go back to our graph again, right? So I'm going to turn off that second picture. So what's going on with our graph as the x's are getting really, really small? Going to 0. Okay? And that's for a big value of b. If I have a small value of b, what's going to happen? They're going to infinity. Yeah. Going up. Now we call this first situation where the b is greater than 1. And really, we should say a is positive, exponential growth. And the situation where a is positive and b is less than 1, exponential decay. No, a could be negative.
Oh, it can't be?
That's okay. So what?
It can't be 0.
Yeah, correct. So what would we say in this situation where the a is negative but the b is bigger than 1? What's that graph going to look like? So let's do that one, right? That's what we have here. Now where a is negative 1 and b is 2. Let's look at that picture.
Yay!
All that happened is we flipped across the x-axis, right? We had the same picture as before. When the a was positive, it just now flipped across the x-axis. So we are seeing that it's decreasing from left to right. We would call this still decay. And what do you think is going to happen if the b is small, but the a is negative? Yeah. let's just take a look at the picture here to confirm that. Turn that one off. Go back to our decay and then make the A negative and see what happens. So again, it's growing, right? But what is it? It appears that that growth is bounded, right? It's never going to get any bigger than 0. So the end behaviors still hold regardless of whether A is positive or negative, correct?
Thank you.
Okay. Oh my.
What was that? Disney spring. Oh. That's it was the best insult of the year.
How about this? Can I say this? F of x equals 2 times 5 to the x. Is that equal to 10 to the x?
No. Because you have to do exponents first. Exponents first. That's the one thing I've carried throughout all these years.
For this to equal 10 to the x, what would it have to be here? If I did that, then it would equal 10 to the x. Without that there, though. What if we had... What is this going to equal? That is 10 to the x.
How is that?
Well, if I have 2 to the first times 3 to the first, how do I do that?
2 times. Oh.
If I have 2 to the first times 3 to the first, what do I get?
How do you know that that's the first?
Well, if I did 2 to the second times 3 to the second, I get 4 times 9, that's 36. Isn't that the same as 6 to the second?
Oh. Okay, yeah.
That rule is going to work for any value of x. What's 2 times 2 to the x equal? Well, you can actually simplify that.
When you take out the 2, you get 2 parentheses, 1 times 1 to the x.
Nope.
No.
So here's the way to think about this. What do you get when you multiply x squared times x to the third? X to the fifth, right? How did you get the fifth there? You added the exponents. So let's do the same thing here. What am I going to get? 1 plus x, not 1x though.
You knew what I was saying.
Maybe, but you definitely didn't say the right answer. You might have known what you were saying.
That's a problem.
Might have been, that's what I meant.
Oh, yeah, you got
But
it.
definitely not what you said, right? Yeah, okay.
Definitely not what you did.
Just to be clear, 1x and 1 plus x, not the same thing, right?
I think I've been going through the last 3 years of that.
That's a problem.
That's an issue right there.
What if we have 2 to the x squared.
I'm feeling like we multiply that one though.
Where you multiply the x to the, so that would be
2x.
equals 2 times x to the second. X times
2x.
2x.
Yeah.
Or what else could you write this as?
2 times x. Oh, never mind. 4. Yeah, I was almost there.
Right? Because you could write this as,
Stop reading out.
okay. What about this? 1/4 times 2 to the x.
That would be
That's
2
Half.
x. 2
1
divided by
half.
x.
Times.
Can't you do 2?
Nope.
Wait, no, 2 divided by 4. 1/2.
No, it's not.
Divided
You gotta
by
do the exponents first.
You didn't take an S, so I don't think it is.
Where's your answer, Bloom?
I know that one, that's the thing. So I'm saying you guys know. Since then, I have the answer.
Well, I want you to think about it. I like where your head's at. You're not right, but I like that you're trying and you're talking it
So
out.
it's not 1/2 to the x.
It's not 1/2 to the x.
Okay.
Okay.
For the exact reason that you said, Olivia, that you have to worry about the exponent before you can multiply the bases.
No, that was good.
So that's the trick that I'm trying to get you to unlearn,
All right. I've
because
got
it's very
nothing.
tempting to try to do something like that.
I've got nothing for this one.
Okay.
Yeah.
All right. What if we, instead of writing it as 1/4, if I write it as 1/2 squared? Does that help?
No. Wait. Yeah. Yeah, it kind of does actually. Watch. I'm thinking do you multiply by the fraction squared?
Nope.
No. I got it.
Okay.
Yeah, I'm stumped.
Well, what if I write 1/2 squared as a power of 2? Right? Instead of writing as 1/2 squared, I just write it as 2 to some power.
Oh, you like flip it?
Well, remember we know that like a to the -1 is 1/a, right?
I got it. Yeah, I'm just not. Where does the -1 come from?
Because
This
we flipped.
this rule
Oh, okay.
is what I'm using.
Make up the back.
Of course.
Thank you.
Okay. And what is that going to allow me to do by writing it that way?
Oh, yeah. Yeah.
So I could write that as 2 to the x minus 2. Now, alternatively, here, you could have also thought about it as this. Everybody's okay there? And what's my rule for dividing exponentials? So numerator minus denominator. So you can think about it that way also. It's doing the same thing, just using different rules to do it. I wanted to do it the first way I showed you because it was using the addition property, or the multiplication property, I should say. So it was just like, the 1, 2 before it or whatever. Is everybody feeling a little okay with our exponent rules?
Yeah.
Okay. So it's important that we're making sure that we can simplify things correctly It's very easy to make those kinds of mistakes. So let's do this example. So f of x is equal to negative 2 times 4 to the x. What's f of 2 going to equal? Let's try to do these with no calculators here. Just to practice kind of applying these exponent rules. Yeah.
Those ACT math questions are crazy.
Oh, yeah?
Oh, yeah.
Okay. Well, when you get your info back, if you want to bring some stuff in and talk about them, I'm happy to do that with you.
So well.
Sure.
But when I get easy ones too.
I mean, you're asking me like to remember what I got on a test from like over 20 years ago. I honestly don't really remember. It was,
Okay.
I think I got like a 29 or a 30, something like that. But like, here's the problem, is I remember that like my English and reading scores were kind of crummy. Like they were like in
Good
the,
thing your math was
In the-
Math was great.
well, like I think I got like a 34 on science and like a 33 on math or something like that.
Oh, geez.
But like my English and reading scores were not good. So to pick back up where we left off, we had this example exponential function, f of x equals negative 2 times 4 to the x. And we were evaluating some examples. F of 0, what does that mean for me to do? So I'm going to plug 0 in for x.
Negative 0.
So what is 4 to the 0?
0.
Nope.
It's 1.
Nope. What? 1. That's right. Any non-zero number to the 0th power is 1. What's 0 to the 0?
0.
Indeterminate.
That's a new one.
It's like dividing by 0.
It's actually different than dividing by 0. It's like 0 over 0.
I meant they're both indeterminate.
Well, dividing by 0 is undefined. That's different than indeterminate. Indeterminate means that I can create like different things that'll all have different values. So I can create something that's like would evaluate to like 0 to the 0 that could be 1 or 2 or 3 or 4 or 10 or negative 7 or infinity, and it's not clear what it should be, as opposed to like 1 over 0, which is infinity, undefined. So if you take AP Calculus, you'll learn more about this, but it's a calculus topic beyond the scope of what we're doing here. No, that's understandable.
Yep, you can math that.
How about f of negative 3? Again, we're going to be plugging negative 3 in for x. So what is 4 to the negative 3? How do I do that?
4 times 4.
Now with the negative sign up there, it's not.
4 times.
Well, come out of
Will not come out as a negative,
try to tell.
right? The negative exponent makes a reciprocal, right? We talked about that in the just a few minutes ago, well, before lunch anyways. And what's 4 to the 3rd? What's 4 times 4 times 4? 64, I think I heard mumbled. And 2 times 1 over 64 is just negative, I'm sorry, negative 2 times 1 over 64 is just negative 1 over 32. How about f of 1/2? Again, we're just plugging 1/2 in for x. So how do I do 4 to the 1/2? That's the square root of 4. Yup, good. Here's a rough one. Well, so we have the question of, like, we have 3 things going on, right? You could think about it as like 4 to the negative 1 cubed and then to the 1/2. Or you could think about it as like 4 to the 1/2 to the 3rd, to the negative 1, or, you know, like 4 to the 3rd to the 1/2 to the negative 1. Really, any order you want to do this is going to be okay. So there's like, there's 8 possibilities of how to do that, right? Is everybody okay there? Yeah. Which one does it feel like of those 3 things to do would be the best one to do first? The 1/2 power, the 3rd power, or the negative 1 power?
Negative 1 power? Or the 1/2 power?
The 1/2 power is what I would do first. Why would I do that first? So, because the square root of 4 is just 2, right? Everybody's okay there? Now that feels much easier, because now, really technically speaking, I could even do this now. And just do 2 to the 1st times 2 to the negative 3 and make that 2 to the negative 2 if I wanted. That's okay to do. Since they have the same exponent or same base, I can just add their exponents. So I can do that. But this is the piece, like, how do I evaluate that, is the piece that I really want to emphasize, right? Like, that I can see that as 3 different exponent operations. The negative 1, the 1/2, and the 3. And it doesn't matter which order I do those 3 operations in. Pick the order that's going to be numerically the most convenient for you. I mean, you can definitely type it into your calculator, but like the point of this was not just doing stuff on the calculator. It was kind of reviewing some of these exponent rules that have been a long time. And when I multiply that then by the negative 2, I get the negative quarter that we've seen. Let's do another example. So here it says the table gives the values for an exponential function. Find the equation of that function.
Where'd you get it?
No, that was.
Shh. Focus. Please. Thanks. So the first thing I'm going to do, because the directions tell me that I'm dealing with an exponential function, I know my answer should look something like g of x equals a times b to the x. Everybody's okay with that? Okay. So my final answer, I should have a value plugged in for a and for b. To do that, which one of these points is going to be most helpful to me? Which one of these points is going to be most helpful to me in figuring out my values for a and b? It's not that one. It's 3 and 0, or 0, 3. Why is that going to be helpful to me? Because I know that anything to the 0 power is 1. And, well, I should say any non-zero number to the 0 power is 1. How do I know that b is not 0? Because this is an exponential function. So I know that b is non-zero because if it's being exponential. So what do I got here then? I have that a is 3. That's halfway down. How am I going to get the value for a now? Or I'm sorry, for b.
You just plug that 3 in the 0.
Well, I'm not going to use that point.
Yeah, you pick one.
I have to use a different one. Which one is going to be the easiest one to use? Which one would be the point that I'd want to use now that I've found my value for a and I'm looking for my value for b? I'd want to use this one. Why is that going to be helpful?
Because your exponent is just 1.
Yeah, it makes b really easy to solve, right? So I just divide both sides by 3. And I get that b is equal to 5. So my final answer is
I love But is it real or?
any question on what we did there? So because of the values we had in our table, that was pretty easy. What if the values in our table weren't so convenient?
Which were we -1.
So again, I know it's an exponential function. So my equation is going to look like this.
Negative 1 is 12.
Which point am I going to need to use?
Both.
I do have to use both of them, and I'm going to have to use both of them at the same time. Because what I need to do,
I do not know that.
so watch what happens if I try plugging in the first point. Right? And then if I plug in the second point, I get that. In either case, am I eliminating either the A or the B?
No.
No, they're both there.
Yeah.
So this is what I'm going to do. I'm going to treat these as, stop talking please, a system of two equations. And I'm going to use this system to solve for B. So what I'm going to do, you guys remember back in the, whatever it was, supplement A, where we solved systems of equations, right? What were the techniques we used to do that? Substitution, elimination, right? So we're going to use the same techniques here. What's different about this system than the systems we dealt with before? They're not polynomial, the equations, very good. Notice specifically that the variables are being multiplied together instead of added or subtracted, right? So if my variables are being multiplied, to eliminate a variable, instead of adding and subtracting the equations, I'm going to have to be multiplying or dividing. Okay? So what I'm going to do is I'm going to take equation A and divide it by equation B. Does it matter which one I divide by the other? No. But can it make your life easier if you're careful? Yeah. So what did I look at to decide which one I want to divide by the other? The bigger exponent of B should be the numerator. -1 is bigger than -3. That should be the numerator of my division problem. Oh my goodness, I wrote it the wrong way. I want to do B divided by A, excuse me. Everybody's okay here? So when I do B divided by A, I divide the left-hand sides together. So that's going to be 12 over 48. And then the right-hand sides together, that'd be A times B to the -1 divided by A times B to the -3. What is 12 divided by 48 reduced to? 1/4. Good. How can I reduce A times B to the -1 over A times B to the -3? I can, yep, so the A's will cancel out, and then Dwan says I can subtract the exponent. So it's numerator minus denominator. So that's going to be B squared. And then how am I going to solve for B? Yep. Now when I square root both sides, I need to use a plus or minus, but this is an exponential equation, right? What do I know about the values of B in an exponential equation? They're greater than 0, and they can't equal 1, so we'll just drop the minus from the plus or minus. So there's my value for B. Now that I have that, I can plug this back into either equation A or B. I'm going to choose to plug it into B to solve for A. What is 1/2 to the negative 1? It just makes the reciprocal, so it just turns into 2. Yeah, the negative 1 exponent just makes a reciprocal, so it just turns into 2. So I divide both sides by 2, and I got my everything I need. Everybody okay with what we've done here so far? Okay. Notice in these two different problems that the value for b, the base of my exponential, in the second example is 1/2. In the previous example, it's 5. What if I told you there's a way to do this so the base of our exponential is always the same number?
That's crazy.
It is crazy, but it's true. What number are we going to use? What do you think? We call this number the natural base. Or sometimes we refer to this as Euler's number. That name, E-U-L-E-R, is pronounced Euler. He's a rather well-known, I think, German mathematician. He's back there on the wall somewhere, I think. Yes. Last column, second row. Column on the right, I should say. Now this number, Euler's number, is actually an irrational number, like pi. So rather than writing the number down, we use a symbol to represent this number. The symbol we use here is the E. That is correct. And the way we find this E, you may, is we look at this limit. Now, this is not something that with our background, God, can we just we can evaluate using oh, darn it. Using algebra or whatever, we have to just do this numerically. So what I'm going to do is I'm going to pick some values for x, and then I'm going to evaluate that limit at progressively larger values of x. So when I plug 1 in for x, I get 2, and I'm just going to do that for a long time. I mean, how many x's do you think I should plug in? About 1,000?
1,022.
Yeah. So if I do that, look at what's happening to that output. It's like pretty frozen there at 271695. That last digit we're still waiting to kind of pin down or whatever. We can give more decimal places, and we could give, the computer will take a whole lot of decimal places, but this is an irrational number, so it's never going to settle down to a single decimal place. It's going to go on forever. But 4 decimal places is probably good enough for anything we're going to need to do. So just for your reference, you do have this number built into your calculator. If you press second and the division sign, you'll get the E, or if you press second and the LN button, it'll give you the E with an exponent built into it. So if you needed to do like E to the 1.5 or something, it's just like, but you could do the same thing if you did like second division and then did the exponent, it's just like saving yourself buttons or whatever, but everybody's okay with this? I'll talk about a little bit more where this comes from here when we talk about some application stuff later on. We'll talk about the motivation behind where that value for E comes from. So what this allows us to do is to rewrite our exponential function instead of f of x equals a times b to the x, where a and b are, b can be anything that's positive. And not equal to 1, we can write this as f of x equals, a times e to the kx, where a, again, is not equal to 0, and k cannot be 0, but any other value of k is all right. What's nice about this new definition is that the base of any exponential is now represented with the same number, e. So it makes it very easy to compare two exponential functions if they have the same base.
We have E on it.
I just showed it to you while you're talking to your friends and not paying attention. You were the friend she was talking to, just so you know. I'm sure you don't know where it is either.
Mic drop.
At least we can say it with a smile, right?
At least we can just own it.
Yeah, absolutely. So we remember to figure out whether things were growth or decay, really we're looking at the values for A and B, right? If we look at this new form, though, what is going to be the important parameters? Is going to be K, right? So something K is going to be exponential growth, and something of K is going to be exponential decay. What values of K are going to give us growth?
Above 1 or above 0?
It's going to be above 0, yeah. So the way you'd think about this is e to the K is like the base of your exponential. So as long as that number is bigger than 1, you're going to be okay. If I pick a value of k that's positive, if I take a number, positive number, and I raise it to a power, I'm still going to get a positive value there. And then what do you suppose decay is? Less than 0. What about k equals 0?
That'll just give us a flat line graph.
Can't happen, right? We didn't allow it as part of our exponential because it gives us a constant function. That's exactly right. All right. Let's do an example.
Do it. You do it. More
All right. Given that the population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people?
I feel like I remember doing things like that.
T there.
Yes.
So when I read a question like this, I think of this problem as a two-step problem. Step one, I'm going to need to write a model, an equation to describe what's going on. And in step two, I'm going to be solving that equation, in this case, for my model equal to 1 million, for some value of t. All right, so let's start here. We're told the population growth is exponential. What is that going to give us? What does the population growth being exponential give us? Tells us that the model that we should be using is one of these two. Does it matter which one I choose? No, man, not really. I'm going to choose this one. Because I think it's probably for us easier to use. Okay. All right. Then we're told the population of a certain city in 1990 is 782,248 people. What is that telling us? these x's here for a minute. So that's telling us that in 1990, the population was this. That's like a point, right? What is it? The next sentence telling us? The population of the same city in 2000 is 895,193. That's just another point, right? Does everybody see how I've unpacked this problem that sounded quite different than anything we've seen before and turn it into something exactly like example 3? So far, so good? Not going too fast? It's okay? I'm trying to be careful in doing this neatly. Now, what would make this problem even easier? Smaller numbers, specifically what numbers would be smaller? The x. What would be a nice value of x to have?
A nice one.
What? 0 would be really nice, right? So what we're going to do is we're going to redefine this, and we're going to say let t equal the years after 1990. So what does 1990 become then?
1.
No, 0. And what does 2000 become then? 10.
Thanks.
Why is that helpful?
I'm not sure.
Well, remember, if I go and I plug in this point, I'd have 782,248 is equal to A times B to the 0. What's B to the 0? 1. And A times 1 is just A. So by recasting x, or recasting the new variable t as the years since 1990, we're able to basically get the A value for absolutely free. That's pretty nice, right?
That is nice.
Okay, how are we going to get the B then?
Oh. Oh, Bart knows now. Oh. Enlarge.
So I can take my other point and plug it in now that I've solved for A, and use this equation to solve for B. What am I going to need to do to solve for B here? Okay, divide both sides by, yeah. Hold on a second, I want to finish this part up real quick. So I divide those two, then what? That's going to give me B to the 10th. How do I get rid of the 10? On the B.
I like the 10.
The 10th root, yeah. So if I press math, option 5, I can edit that, make it a 10 of that previous answer. And there's my value for B.
Oh.
Boom. It went up. He went. Oh, shut up.
That was like a
You're so nasty. Oh, wait.
We'll finish this up next time.
I am.